pretty messy, so we I didn't want to use 1 root 2 because I wanted whole numbers, because I don't like working with square roots, because then I have to do a calculator. If it's whole numbers, I can do it in my head. Max is my favorite, let's be honest. All right, that's not true. That's not true. I quite intensely dislike him, in fact. Yeah, gotta cover my tracks. I'm gonna start asking questions. All right, be quiet. So, example 2, repulsive charges. We've got a pretty complex scenario here. I mean, it's nice that it's a right angle, a isosceles triangle, but that doesn't do us too many favors, really. The question itself is going to be stated as find the force and subsequent acceleration, and I'm throwing a little curveball at you with that one. Acceleration of charge 2. Actually, scratch that. Don't do that. All right, let's do it. We're gonna do something a bit weird here. We're gonna call charge 2 a proton. It's not, because protons don't have a charge of 5 microcoulombs, but we're just gonna pretend it has the mass of a proton, and that'll come up later. Okay. All right, are you with me with that? So charge 2, we're calling it a proton. It's not really going to be a proton, but we'll pretend that it has the mass of a proton. All right, hardest thing with these problems, guys. Hardest thing is starting them. How are we going to start? Campbell, how would you start? Exactly. Tanika, how would you start? Yeah. Come on. What would you do? The formula. What formula? The formula. You would go straight to your formula. You know that force, which is what we're looking for, equals 1 on 4 pi epsilon 0 times by QQ over R squared. You know that formula. You're looking for a force, you're going to use that formula. Now, when we talk about this formula, it only applies for 2 charges. We've got 3 charges here. What are we going to do, Brandon? Huh? Yeah, just pick 2 charges and do the math for those, and then pick the other 2 charges, do the math for those, and then do vector addition, because this is all vectors, right? Forces are vectors. You know that you're going to end up with 2 vectors. Now, you can stop at this point, once you've written down that formula and reminded yourself, oh, this is one of those questions, you can stop and have a look at it and go, well, what is going to happen to that charge 2? What's Q1 going to do to charge 2, Rebecca? Someone have a look. Q1, positive 7 mic. Oh, no. Is that the first time that's happened, though? It's because you're in a senior jersey. As soon as you come into my class in a senior jersey, I do it. I didn't do it at all last year, did I? Oh, did I? You just never pulled me up on it? Okay. Sorry, Michaela. I just thought you really weren't ready for that question. Yeah. Look, I apologize, all right? You're much better than her. Yeah. So much better, you're going to answer my question. What's going to happen to charge 2 as a result of charge 1? Just roughly, not exact values. Yeah, they're going to be repulsive. So which way is charge 2 going to be sort of forced? Well, if charge 2 is this one, and charge 1 is this one, and they want to move away from each other, it's going to go down, right? Charge 2 will be forced straight down. Yeah? However, charge 3 is going to have an effect as well, Sam. What's charge 3 going to do to charge 2? It's going to pull it. There's going to be an attractive force. So which way is it going to be forced? Right, this way, but then, yeah, like you said. So let's just think about that. Kobe, you're going to be quiet for me for a second. And Hannah, you too. Nice and quiet for a second. Let's have a think about this. Let's call Q1 our purple Q. Fabulous. And Q3 can be our orange Q. Okay. And we're going to see a force on Q2 from Q3 like that. And we're going to see a force on Q2 from Q1 like that. Here's another question for you. Which force is going to have a greater magnitude? The force from Q1 or the force from Q3, Nicola? The force from Q3 is going to give it a greater magnitude of force to Q2 because it's got a greater charge, and we know that it's just the product of our two charges. So if we have a larger charge in our numerator, we're going to get a larger force as a result, right? And that makes sense as well. There's a stronger charge there, there's going to be a stronger attraction. So it's going to mostly go to the left, and it's going to be nudged down a little bit. We're going to have to find the magnitude of those component vectors to find a resultant vector. Yeah? That's what we're doing here. Whether we do it algebraically or visually, it doesn't really matter, okay? Let's call this force, and I'm going to say 2, 3. And you can see now why we generally use letters to label charges, not numbers. And I forgot because I had my headspace somewhere else. And we're going to call this one force 2, 1, not 23 and 21. 2, 3, and 2, 1. You can chuck a comma in there if you want. Can you guys even see that, or is that a bit too small? I'm pushing it, aren't I? Hopefully it's legible. Okay. Force 2 due to 3 and force 2 due to 1. All right, let's do the math now. Do you guys need me? You can do this, right? Remember, correct communication, sub in the correct notation. You're not using capital Q and lowercase q here. We've given you labels for these charges. You're going to replace capital Q and lowercase q with the relevant Qs that you're talking about. If you just take that formula and then you sub in 7 and 5, I'm going to be like, well, what about 10? Why is capital Q can be 10 as well? You need to communicate that, all right? I'm going to do a little roam. I'm going to pause my recording. So we're going to have two formulas. Q1, Q2 over the radius between Q1 and Q2 is 1 centimeter, so that is 0. Or we'll just say radius for now. 1, 2. Now remember, every time we do one of these questions, we're being reminded that radius squared is our relationship here. It's an inverse squared relationship. Don't forget that. That is important that we recognize that. And that's the force of 2 from 1. Find the force of 2 from 3. 1 on 4 pi epsilon 0. Q3 on Q2. Divided by r squared between 3 and 2. Hey, how come someone was asking me how to convert root 2? You know you don't need to use it, right? Yeah, all right. Yeah. I didn't really think about that either until just then, and then I was like, oh god, they're not using that as their radius, are they? Okay, so force 2 on 1. Q1 is 7, Q2 is 5, 7 times 5. It works. You don't even need brackets. You'll just get 0.00035 or whatever. 10 to the negative 6. Sorry guys, I've done that a couple of times over the last few lessons actually. That's 7 times 5 in brackets like that and then times by -6. I'm used to doing that because I'm used to doing it for uncertainty where we say, 6.3 plus or minus 0.1 all in brackets times whatever. I actually can't do it here. It's not the same thing. 7 times 10 to the times by 5 times 10 to the this is multiplied twice. But like that, you'll get a much larger answer than you should. Sorry, I've done that a couple of times, so be careful. If that's in your notes from last lesson as well, you might want to correct that. That is not correct. Thank you. Oh, we were just talking about converting a square root. That would look like, but then I realized involved in any of this. No, we're doing. We're only finding the charge.
Yeah, I thought that was 1 and 3.
Yeah, sorry, so good pickup. So make sure we make that correction. We cannot do 7 times 5 like that. Seven by 10 to the negative 6 times by 5 by 10 to the negative 6. Has to be done out like that. I'll just quickly correct that in our notes from last lesson too. I did it here as well, see? So if you got those notes down from last lesson, I've actually done it wrong. I think I checked my answer in the textbook, so I probably ended up, you guys did it right, and we ended up with the right answer, but that working is incorrect. 5 times negative 5. 5 times. Is that the only time I did it? No, I did it here as well. I am hearing way too much of this conversation, and I feel like I don't want to. I mean, I'm recording. Whether it's picking it up or not remains to be seen. That was my low-key way of saying, can you talk about it at lunchtime? All right, what sort of numbers did we get for each of the forces? Who can tell me force of charge 2 from charge 1? 3,150 newtons. Negative 4,500 newtons. Do people agree with that? Anyone make any mistakes that they want to check what they did or how it worked or what happened? Cool. Now, forces are vectors, which means let's specify what these numbers mean. This one, being positive, is repulsive. And in which direction? Down. Yeah? This one, being negative, is attractive, meaning left. Okay? Or yeah, north, south, east, west, whatever. Give me true bearings. I don't care. You guys have a million ways of doing this from mathematics that you know of. You're doing vector stuff again now, are you? In methods. You did it in specialist in year 11. Start of year 11, you do nothing but vectors then. Yeah. 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 So remember, when we do a lot of this math, and especially when we use things like Pythagoras and stuff like that, the positives and negatives don't necessarily mean anything at those points. So we have to analyze at the start and we have to analyze at the end. There are those situations where negatives actually have to be considered to give us the answer, like when we're doing projectile motion, because we are using negatives to reference a coordinate plane. So, if we say our displacement is down 30 meters, that matters. If we throw a ball up and then it lands, it will land earlier if it lands 30 meters positive than if it lands 30 meters negative. So our formulas will actually take that into account. But right now, this isn't projectile motion, so we're not necessarily predicting a Cartesian plane with this formula. This is just predicting the force of the magnitude, and to some extent it tells us attractive or repulsive. I think as a general rule, if it has radius in it, you can kind of ignore the plane because you're not talking about X, Y systems. You're talking about positions in space. Yeah. Don't use that as gospel though. All right, cool. Are we done? No, of course not. Hands up if you are finished and you have a total force. Yeah? What did we get? Can you read it out to me, my favorite student ever, Max? 2 newtons. 92, 93 if you round, which you probably should, so 93 newtons. Yeah. People got different things? No. So let's look at what we actually have here. And this is where we are going to go to our Cartesian plane. We have charge 2, right? This is Q2. We have 3,150 newtons down. So this is force due to 2 from 1. And it's equal to 3,150 newtons. Then we have, this is force on 2 due to charge 3, and it is 4,500 newtons. We're ignoring that negative intentionally now because we've given it direction rather than having a positive or a negative value. So we could have done it back here. We could have corrected it back to a positive there, but it's fine to say negative 4,500. That's telling us that it's attractive, as we've discussed. So we now need to find a resultant vector. No, that's not what you do. Yeah.
It doesn't matter whether you.
That's actually wrong, actually. Ignore that. Hang on. God, it's been a while since I've done some of this stuff, guys. Oh, no, that is how you do it. Sorry. Yeah, no, that's fine. Second guessing myself. So generally, our rule for vector addition is tip to tail. Yeah? Generally, that's the rule we use in physics. So we move this one over like that, and we do tip to tail. But it doesn't have to be like that. You can just take the x, y components of each and add them. Okay? And we end up with what? Right, because it is c. C squared equals a squared plus b squared. Did you know this is exactly the same in 3 dimensions? You just add a third thing. C squared equals x squared plus y squared plus z squared. So all this stuff you're doing in physics, if you're doing the math that teaches you how to do it in 3 dimensions, you can do the physics in 3 dimensions as well, which is pretty cool. C squared equals a squared plus b squared. So C, which is of course our total force, equals the square root of 4,500 squared plus 3,150 squared. Is that what you had, Max? And correct answer, confident? 5,493. It looks right to me. It makes a lot of sense. Holy crap, charges are strong. That's microcoulombs. Crazy. Bring microcoulombs within a centimeter of each other and they'll put 5,493 newtons of force out. Do you know how much force it takes to lift like a 100-kilo person off the ground? 980 newtons. Force equals mass times acceleration. Acceleration due to gravity is 9.8, or if we round it to 10. Wait, yeah, 9.8, either or. If they weigh 100 kilos, 9.8 times 100, 980. That's just to levitate them, to be fair. If you applied 5,493 newtons, they accelerate pretty quick. Yeah, true. They'd probably disintegrate into their blood and guts. This is charges coming into close proximity of each other. Now, have we answered the question? No. What do we got to do? Right. Hence why we're having a conversation about a 100-kilo guy, except we're not talking about a 100-kilo guy being thrown around because he's not a charge. What charge are we talking about? Proton. Thank you. Find acceleration. My point that I wanted to make by doing this quick extra bit on this example is that kinematic equations, those laws of linear motion, projectile motion, all that stuff, works. It still works. It works perfectly. The one complication is that the forces don't go away. It's not like hitting a ball with a bat. When there's electric charges, the forces are present theoretically infinitely. So at this distance, it's been accelerated, but then it gets accelerated less, then it gets accelerated less. But it's still accelerating, whereas you hit a ball, you give it that instant acceleration, and then it's just decelerating. So things are a little bit weird. But the acceleration at this point is F equals ma. Newton's laws still apply. Rearrange to give A equals F over m. The force is 5,493 newtons. The mass of a proton is in your formula and data book, I think. Yeah, what is it? I stopped listening after you said 1. Say again. Yeah. All right, now you're just being condescending. Wait, that's a 7. I stuffed up. Go slower.
Okay. 1.6.
26219. Is that in kilograms? Cool. How quickly does our proton accelerate? Come on, give me an answer. It's like times 10 to the 31 or something? Times 10 to the 30? And what's the value? Give me 1 decimal place. What? That's not a decimal. 3.3 times 10 to the 30 meters per second squared. Woo! Be fast. All right, now the reality is charges on protons are incredibly small, well below the charges of microcoulombs. Let's have a look at that real quick. Check this out. I'm pretty sure the textbook has a list of common approximate charges. Or am I making that up? Does your formula and data book give you the charge on an electron? It does, right? QE? What's that? In magnitude. Just by 10 to the what? What's its order of magnitude? By 10 to the negative 31. No, it's charge. Negative 10 to the negative 19. Yeah, so I mean, we're talking about charges with by 10 to the negative 6. This is 13 times, or no, sorry, that's not how it works. 3 times smaller in charge than that. Is that how it works? No, it's 13 times smaller than that. Yeah, I think so. Anyway, point made. How are we feeling about that sort of question? Feel like you can do it? Cool. Let's go back to our exercise then. Remember, question 8 is a little bit kind of optional-ish. Thanks, guys. Finish off those questions this lesson. We won't come back to these. Let's go.